Example 2. For what values of P is the series the sum from n equals 1 to infinity of 1 over n to the power P convergent? Solution: if P is less than 0, then the limit as n approaches infinity of open 1 over n to the P close equals infinity. If P equals 0, then the limit n approaches infinity open 1 over n to the power P close equals 1. In either case, the limit as n approaches infinity open 1 over n to the P close does not equal 0. So the given series diverges by the test for divergence. Open 11.2.7. Side note: in order to use the integral test, we need to be able to evaluate the integral from 1 to infinity of f of x dx, and therefore we have to be able to find an antiderivative of f. Frequently this is difficult or impossible, so we need other tests for convergence too. Continuing the solution: if P is greater than 0, then the function f of x equals 1 over x to the P power is clearly continuous, positive, and decreasing on open bracket 1 to infinity close. We found in chapter 7, see 7.8.2, that the integral from 1 to infinity of 1 over x to the P dx converges if P is greater than 1 and diverges if P is less than 1. It follows from the integral test that the series, the sum from 1 over n to the power P converges if P is greater than 1 and diverges if P is less than or equal to 1 but greater than 0. For P equals 1, the series is the harmonic series discussed in example 11.2.9. The series in example 2 is called the P series. It is important in the rest of the chapter, so we summarize the results of example 2 for future reference as follows. 1. The P series, the sum from n equals 1 to infinity of 1 over n to the power P, is convergent if P is greater than 1 and divergent if P is less than or equal to 1.